we want to thank the National Science Foundation Office of Polar Programs for their financial support to ARCIS and for this seminar series. Now I'd like to welcome our speaker. Dr. Holzworth has been a professor of Earth and Space Science and adjunct professor of physics since 1982. He did his undergraduate work at the University of Colorado, majoring in physics and math, and received his PhD in physics from the University of California, Berkeley in 1977. He was a member of the technical staff at the Aerospace Corporation, Los Angeles for 4 years before moving to the University of Washington, where he manages an active teaching and research program in atmospheric electrodynamics and space plasma physics. Dr. Holzworth has published over 150 peer-reviewed papers. As an experimental physicist, he has been the principal investigator for many high-altitude balloon experiments, several rocket payloads, and a few satellite payloads. He is the director of the Worldwide Lightning Location Network, or WWLLN, a global ground-based lightning location network. In the past few years, Dr. Holzworth has been the principal investigator for research supported by the National Science Foundation, NASA, the Air Force Office of Scientific Research, the Naval Research Laboratory, the Defense Advanced Research Projects Agency, or DARPA, NOAA, and the European Commission. He recently delivered a vector electric field instrument to NASA for a Naval Research Laboratory rocket payload to study ionospheric plasma waves. The launch is planned for summer of 2022. And his instruments on the Air Force NASA Communication Navigation Outage Forecasting System satellite recently re-entered after operating for over 8 years. Dr. Holzworth finished his term as chair of the Council of Institutions of the University Space Research Association in 2016 and remains the representative from the University of Washington to the University Space Research Association. Please join me in welcoming our speaker, Dr. Holzworth. Dr. Holzworth, we'll turn it over to you now.
All righty. I'll set up the screen share. And hopefully this will, there we go. Well, thank you all for coming. And if you can't hear me, yell or tell me so I heard everything else going on. I got interested in this topic of lightning in the Arctic from basically hearing and learning about the global warming process going on and how much more intense it was in the Arctic than it was for the planet as a whole. So I started to look at our data and came up with some interesting new information. And that was the beginning of this research project. So I'm going to talk about give you some background of what the connections between the climate change and global lightning. Is this thing in the way for you guys? I don't know if that helps. And also talk about the background for how we actually make these global lightning measurements. And then give you the evidence that we have collected for Arctic increase in lightning in the Arctic. And the interesting for me, it's one thing to count lightning strokes, but it's another thing to try to understand their connection to geophysics and understand what's going on. And so we found that there's a direct relationship between the global temperature anomaly variability and the variability of lightning in the Arctic. And so then we'll talk about predictions about what might happen in the future. So if I can get this to work, there we are. As you all know, probably much better than I do, the Arctic is warming up. On my screen, by the way, I can see all the faces at the bottom of the page here. Is that blocking the screen for you guys?
Hi, Dr. Holzworth. That's not something that we see. We just see the slideshow itself.
Okay, perfect. So this is just one of those, very dramatic. I'm really interested in figures that, in one view, tell a story. And I think this is one of those figures that basically says, the extent of the ice pack in the Arctic has just been steadily going down this whole time. And it just makes so much sense that it's being affected by global climate change situation as the ice melts. There's a feedback mechanism because the water then absorbs the solar radiation more readily than when the albedo goes way down and so forth. So the whole Arctic is warming up and fast. We have the other direct evidence that we see about on TV and normal people that don't have a science background hear about is finding the animal tusks and things like that in the permafrost, and how the permafrost is melting and the buildings are collapsing into the ground and so forth. So all of this goes together to say, hey, the Arctic is really warming and really warming fast. So let's see what we have. We've been measuring global lightning. We've been detecting global lightning for longer than any other real-time global lightning network, since we have data from 2004. But the satellite data go back even before that. Only problem is that the most of the satellites are like the current version of the optical sensor on the International Space Station, the lightning imaging sensor, which only looks at the ground in one few hundred kilometer square size as the satellite goes around in low Earth orbit. So it doesn't really pass over the same place on the ground more than once every couple of days. So it doesn't have any ability to really track storms very carefully. Or you get the climatology like this figure from just 3 years of data from the ISS LIS instrument, which by the way was the spare that was built for the TRIM-LIS instrument. The TRIM-LIS satellite went around for quite a long time before this, and it finally died. And they put the spare instrument on the ISS some years ago, and it's working fine. And it's great to have a continuity of that. And you can see what we all know, which is that there's more lightning over the continents than over the oceans typically. But the problem is you can see how pixelated this is. So we developed a lightning network. Oops, where do we go here? Come on, down. The Woollen Worldwide Lightning Location Network developed back in the early 2000s. And with this, we see, orders of magnitude more actual strokes than the satellites, the low altitude satellites would see, because we're looking at the whole Earth at the same time in real time all the time. And this is a climatology map of the world showing basically the same thing you saw here, that there's more lightning over the continents and less over the oceans. And that's true, although now we can see with much finer resolution interesting features. Like here we have, let's see if I can, maybe I can get a pointer option. How about a laser, a pen? All right. Let's see if you can see my pointer better. No, I don't see any point. Oh, nope, that's too small. Sorry, get a better pointer. There we go. Can you see my laser pointer now? Is that showing up on the screen?
Yes, that's showing up. We can see that.
Okay. So, so now we can see with much finer resolution the intertropical convergence zone and the lightning that occurs over that. We can see the distinct differences between the blow off of the continents like South America, Africa, and the Australia regions, where there's this these cloudy features that develop and blow off the continent and carry convective activity out over the oceans there. You can see a lot of little details that are helping us understand better the local climatology all over the planet. As a space scientist, my reason for being interested in this was that there was no, prior to this, there was no sort of real-time global source function. you may not know, but lightning generates an upward propagating Whistler wave. Every single lightning stroke generates an upward going lightning Whistler wave, a lightning generated Whistler wave in the ionosphere, which propagates out into the magnetosphere. And so the question about interacting with the space plasmas from lightning generated waves was one that has been intrigued me for years. And so this was one of the my motivations, being a space scientist, to work on developing this network. Well, I'll talk about more about Woollen in a little while. But as you can see from this figure, this red line is at 65 degrees north, and there's a lot of lightning up here in northern Alaska, northern Europe, all across Siberia. So there's plenty of lightning up there at places where the satellites just don't get to. Satellites in typical orbits like the ISS are at 55 or so degrees inclination, and the instruments can see maybe 10 or 15 degrees beyond that. So maybe 70 degrees is the furthest north that you can see from those polar orbiters. And also the new geostationary lightning mapper, which only covers the Americas, only sees up to about 65 degrees north. And there's almost no lightning below about 55 degrees south, because you run into the southern oceans, and then you run into the ice pack on Antarctica, and none of that is very good for generating lightning. Convection, severe convection doesn't develop down there very well. So we decided to use the Woollen lightning data up here north of 65 degrees to look at what the time variations might be for the region. One of the first things we noticed was this. This is a plot of just individual lightning strokes above 75 degrees north. And what you see are several features already. One is that over here in the Western hemisphere, there's not as much lightning over northern Greenland and the ice pack north of that, or over the Canadian islands and the ice pack north of that. You don't get nearly as much lightning over here as you do over here in the Eastern hemisphere, north of Siberia and Europe, where there's a lot more lightning in the Arctic than there is in the other hemisphere. Also, you notice that there's some lightning all the way to the pole. And in fact, there's one nice event that we've been looking at, which occurred a couple of years ago with within 100 kilometers of the North Pole. So lots of lightning, even lightning at the North Pole, at or near the North Pole, and throughout this region of both the land mass and the oceans, the Arctic Ocean near the land, especially on the Western Hemisphere. Now, I can talk about this later, but the region of the Arctic Ocean is a interesting one, and it's fed by water, or it communicates with the oceans through the Bering Strait and through the Fram Strait and northern Atlantic. But the North Atlantic feed into the Arctic Ocean is like 2/3 of the water that circulates in the Arctic, and it's warmer. And through the Bering Straits, you get a lot less of the total water that circulates into the Arctic, and it's cooler because the Bering region, I think, is shallower, and it doesn't carry as much heat energy into the polar regions. But I'm not an oceanographer. However, I can talk about that a little bit later. Okay, so what did we find? Here's the first sort of summary of our data. This goes from we did a study using about 10 years of data from 2010 to 2019, and we've extended that. I'll show you a couple of slides that help extend that a little bit. This was published in a GRL recently, and so this basically shows that from 2010, the lightning, these are actual strokes detected by Woollen, increased by 200 or 300% from then over this course of this decade till where we are now. So And also there's these high and low variability. So we're wondering if this is just statistical fluctuation or what this might be. And we'll see that it correlates nicely with the temperature anomaly. Okay, so let me talk for a minute about the lightning network, because Woollen is a growing network, and we've been increasing the number of sensors and the coverage and the detection efficiency continuously. But and this shows the total number of Woollen strokes over this time period by the network. This includes everything during June, July, and August. We've focused on June, July, and August, which is basically the only times when you do have lightning that's well up in the Arctic. So, so this shows, excuse me, this shows the total number of lightning strokes to get an idea of how the overall global detection efficiency of the lightning network might be. And what we see is that, yeah, there's this huge increase that actually extends well back here as we were adding sensors and growing the network. But the total number of sensors has sort of stabilized. There's a few places we'd like to fill up gaps, and so we're still growing a little bit. But over this time period, the total number of strokes globally that we're measuring was basically pretty stable from about 2013, varying by just plus or minus a few, 10% or less. Whereas from the earlier days till that time, the increase was at least order of 100% increase from 2010 to 2013, roughly speaking, in terms of and so you can relate this to the detection efficiency of our network. But it's been pretty stable since 2013 or 14. So we use this information to sort of try to normalize the data that we took in the early part of our sample period. And so correcting for this dark blue is the plot I showed you a minute ago of the total number of strokes. And the light blue shows where you would adjust the detection for the decreased detection efficiency back in 2013. And so more or less a factor of 2 increase over the total strokes that we actually measured, but in decreasing above that and very little variability beyond that point. So that with that sort of detection adjustment, we were able to start looking at the variation of lightning and what it might mean in comparison to the global other geophysical parameters and properties. The best way, I think, to look at these data, these are total stroke counts in this figure. But the question is, how does that relate to the rest of the globe? Is it increasing or decreasing? And since we already showed that the total number of strokes is not really increasing, at least not after 2013, we didn't see an increase in total global strokes, not very much anyway, plus or minus 5 or 10%. So the question is, how do we best compare these data to search for a change in the number of strokes relative to the global variability? And this is a plot of the ratio of the number of strokes in the sample region, that is to say north of 65 degrees north, compared to the total yearly strokes measured by Woollen. And so that means it's like a fraction, and these fractions are a fraction of a percent. So this would be 0.5% of the total lightning in the world was occurring above 65 degrees north at this 5 times 10 to the minus 3 point. And we can see a very clean and clear signal, just like the total number of strokes we were just looking at, but as a fraction of the globe, showing the same property, that it was increasing relatively dramatically from down here around 0.02% to up here around 0.06%. So maybe a factor of 300% increase in the total number of strokes in the Arctic over this time period. So that was pretty exciting to find that there was such a clear signal, even though our data set is only 10 years long. Of course, as you all know, the Arctic is the place to be studying this, because it's changing the most rapidly of anywhere on Earth, it seems to me. Okay, so let's see what it compares to. This is a plot that any of you can make. There's the web link at the bottom of the page. Basically, this shows the NOAA accumulated information from thousands of buoys and temperature sensors all over the globe. And basically, it sets a baseline and says what's the variation of temperature above the baseline. So they set it at 0 degrees F in this case, and we're looking at the anomalous increase above the baseline for this 100-year plus period. And this this right-hand side is where we have the data for our experiment, but you can see quite a bit of variability in the temperature anomaly. This is for the whole year, temperature variability for the whole year, January through December. You can select subsets of that, as we have done, but basically you can see from this that the variability has increased from in this case degrees Fahrenheit, sorry about that, to 100 or 1 degree Fahrenheit to almost 2 degrees Fahrenheit. So something on the order of a large fraction of a degree, well, like a half a degree centigrade over that period is what we expect, what we see, what the global data sets show. And so now we want to compare how this variability looks compared to the lightning that we see. And here's that plot. So this shows the plot that I showed you before, which is the blue line of the percent or the ratio of the strokes in the Arctic. And the red line, which is on the right-hand axis, is the global temperature anomaly. And this is for the globe, not just for for June, July, and August. This is for the whole globe. In this particular case, there's some subtle variability, but you'll see that the red line doesn't change a whole lot, or the anomaly doesn't. It's mirrored in the if you just limit yourself to the northern hemisphere summer months as well. But what we see from this is a pretty clear correlation, apparent correlation anyway, between the temperature anomaly as it goes up and down, and the actual amount of lightning that we're detecting in the polar region. In fact, we can plot the two data sets side by side and get a nice plot of the variation of the lightning as a function of temperature. I show this slide to add from the paper the next year, which shows in 2021 the anomaly dropped, but also the amount of lightning dropped. So again, it's the ratio of total strokes divided by the total yearly strokes. And in this case, we're doing just June, July, and August data set. And here we have the global temperature for June, July, and August. So there's subtle differences, but you can see from the red plot that it's almost the same as it was before, a little bit exaggerated from what it was for the whole globe. And we can see a nice drop off. We saw a reduction in the total number of strokes, but darned if we also didn't see a decrease in the actual temperature between 20 and 21 for the whole globe for June, July, and August. So again, it fits very nice. It goes very nicely with the data. You can plot the data as a fraction of the global strokes compared to the global anomaly. And you see something that's got a lot of scatter, but you can almost lay a straight line down on there and see, just use it as a linear prediction method. I'll talk about that in a little bit. Adding the data that we just added the last year or two, you get the same thing. The plot is also basically increasing, and it's a reasonable fit. What was the chi-square was 64%. So I'm not trying to argue that this is causal necessarily. This is just observational, that we're seeing that there's a very clear correlation or apparent correlation between the amount of lightning that occurs in the Arctic as a function of the global temperature anomaly. as the temperature anomaly increases, so does the lightning. And that has been borne out well in a year like this last year, which is sort of like a test of the theory, because the total strokes went down, but also the total, the lightning increase, and the lightning anomaly, sorry, the global temperature anomaly also went down. So to keep things in mind, the number of strokes increased by something on the order of 300% over this time period in the Arctic, and so if this continues, if this process relationship continues, and we just do a linear forecast, then we would say, okay, just continue that line on up. And let's say we go from where we are today for another half a degree C rise. We hear a lot about, oh, when we pass, 1.5 degrees, then, there's going to be a breaking point or whatever. So what's happening to the global lightning? Well, we can predict from just this linear relationship that by the time the global temperature increases another half a degree centigrade, that we will be seeing at least another 200% of lightning in the Arctic region. And that's basically just a simple linear fit. It doesn't include all the other things that are going to happen, like variations in ocean currents, which are no doubt going to be affected by global temperature variations and many other processes. But just taking the data that we have now and projecting forward, we will expect at least another factor of 2 increase from where we are today in the total number of strokes in the Arctic. So that is has been the main focus of what I wanted to present to you, and I've gone through that quick enough so that I can talk about the maybe some of the processes that might affect it for the causes of how for instance, some of the things we've identified in our analysis are the back here on this figure are the big difference between the eastern and western Arctic hemispheres, and how there's a lot more lightning in the eastern hemisphere than the western hemisphere, things like that. So we can start digging into some of the details of what might cause that. And so I'll suggest to you that we'll do that later, since I have time. We'll suggest to you that the way the ocean currents flow tend to bring the Gulf Stream, which curls around and keeps England and northern Europe warmer than it would otherwise be, generally speaking, flows into the Arctic and tends to warm up, bring warmer water into the eastern hemisphere side of the ocean. And by the time you get over here to the western hemisphere, you're bringing in water through the Bering Strait, which is cooler. And so this whole side of the western side of the Arctic is a lot cooler, but ocean temperature wise, and therefore the ice is not melting there as rapidly, and it doesn't have the feedback of when the ice pack disappears. Doesn't have as strong a feedback when the ice disappears, that you have the much increased absorption of insulation in that region. So that's a nice feature. Let me see if I have. Yeah, here's a figure that we see from. I think this is from Woods Hole. Let me see if I can move that out of the way. Oh no, this is a NASA figure, but basically this shows for the last summer and the winter, the Arctic region. And basically what you see is that even at the end of the summer season, you still have ice pack that's pretty close up against the Canadian islands and Greenland, but there's a lot of open ocean all the way around the other hemisphere. So that adds to the notion that over here we're going to have more opportunity for convection to develop, and therefore, more of a land-ocean interface, land-ocean contrast. And so differential heating will be enhanced, and convection will increase, and you'll have more chance for lightning to develop in the summers, especially in the Eastern Hemisphere side of things. That's just one contribution that we can make from having noticed the lightning and compared that to the ice pack during this time period. And so I wanted to talk a few minutes about how the Woollen lightning network works. This is from yesterday. This basically shows the globe. We make this plot every half hour, and it shows 40 minutes of lightning data. So the dots, the green dots, are the most recent 10 minutes, and that fades back to the red dots, which are like about 40 minutes before. And so that's where lightning was occurring yesterday for this time period. And the white circles with red asterisks are where we have stations that are active. Also, you might be interested to know that one of the things that makes Woollen work so well is that we have 5 stations active in Antarctica, so that we can triangulate much better. We have a way to tie down the southern end of our time of arrival measurements from looking at lightning waveform data. Lightning makes a channel like an antenna in the sky and radiates radio waves into the Earth atmosphere waveguide, which are then detected all over the Earth at all of these locations. And we have stations in Russia, don't tell anybody, and we have stations in the Americas and Indonesia, Antarctica, and so forth. And we have less coverage in Africa, but turns out that it's not hampering our detection efficiency that much, because the typical lightning stroke, here's an example, sends a radio wave that is detected by stations, often well past the quarter way round. The Earth is quarter way around is 10,000 kilometers. So typical lightning strokes, these are from the Boguslav volcanic eruption that occurred a couple of years ago. And this is just one stroke. So this shows the great circle paths of this one stroke to where they were detected by stations in Japan and Europe and all over the North America and even down into South America from this one that's just one stroke. So that shows that with a network, as I described in this figure, we can detect lightning all over the globe in real time and watch it vary with just a set of passive sensors all over the Earth. And we get data set that is 1 to 2 orders of magnitude more actual total strokes than the polar orbiters produced for when they were measuring lightning from space at low Earth orbit. The geostationary lightning mapper is more sensitive than Woollen in terms of being able to see a lot of the small strokes. And that'll actually be good, because we can help calibrate our network relative to the, at least to the Americas, using those data to get a better idea of the small amplitude strokes that we may be missing. But still, we're seeing lightning that covers the globe, and our detection efficiency above about 40 kiloamp peak current is close to 90%, 80 to 90% of total strokes, especially cloud to ground strokes, because they tend to be larger than in cloud strokes. And so the lightning network allows us to really study the temporal and spatial variability of lightning all over the world, because the sensors can see lightning that comes from actually essentially all the way around the world. You can have lightning that generates a lightning radiation pattern that is detectable at the antipode for large strokes. So lightning propagates really well, especially across the water. Water is a good conductor. Oceans are a good conductor. And so propagation across the oceans allows you to propagate. That's why we see these strokes that were detected in Europe through the Bering Strait, because the Great Circle paths here are mostly over water till we get down to over Europe. So that's basically how Woollen works. Is it uses radio wave detection for our stations, and then uses the GPS to give accurate timing, and then reports the time of the arrival of the group velocity of the radio wave at each of these stations. And this is one of my favorite figures. This was produced by Abe Jacobson, and these are lightning strokes from as detected from the satellite, the low Earth orbit satellite, the CNOF satellite. And this is an energy plot. So there's a spread in energy that's a couple orders of magnitude. But basically what you can see is each of these strokes was located by Woollen. So he took the lightning measured on the satellite. In this case, these are radio wave measurements on the satellite from electric field sensors, and watch the variation as a function of distance, arc distance to the stroke. So Woollen located the strokes, and the satellite plotted just the intensity as a function of, or the energy. Basically, it goes as E squared, so it's proportional to the energy or the power as a function of the distance the way stroke is. And the cool thing about this figure is you can see that once you pass 10,000 kilometers, there's a reconvergence, as you would expect, because the lightning radio wave spreads out globally, but then once it passes quarter way around, then the wavefront reconverges and it gets larger. And so when the satellite was detecting radio waves that were more than a quarter way around the Earth, more than 10,000 kilometers, there's a reconvergence, and so the signal seen by the satellite was increased, which you would expect, and that was really nice to be able to see. But this shows that we're seeing lightning all around the world, all the way out to this is the antipode, 20,000 kilometers away. So the lightning that's seen on the satellite, this emphasizes the first thing I said about my interest in space physics and the lightning, is that we really see every lightning stroke makes a upward going Whistler wave detected, in this case on the satellite, and even from all the way around the world. You can have lightning strokes that are occurring right now, and they could be seen all the way around the world in the ionosphere. So these are Whistler waves. These are plasma waves that are generated by the lightning that propagated all the way around the world. And then we know that it didn't reach the satellite by propagating from the stroke to the satellite. It first propagated in the Earth ionosphere waveguide, and that's because of Snell's law. Some of you will know that when you have a refraction from light that propagates into an increasing density, so the radio waves are propagating upward into an increasing ionospheric electron density, and so the wave normal is rotated towards the normal. The wave velocity propagates and rotates towards the normal vector. So the normal vector is a vertical vector, and so as the radio wave moves up through the ionosphere, the low altitude ionosphere, it rotates up till it's almost vertical. So it's coming out vertically. So all of the radio waves that are making from lightning, that are making Whistler waves, those waves propagate through the ionosphere, and when they come out the top side of the ionosphere, they're propagating almost vertically, relatively close to vertically. They're not propagating like in the direction that came from way around the globe from that lightning stroke. So that's the nature of what's going on with lightning in the ionosphere as it propagates upward, and it's also become the source of a lot of interest in how it may be affecting the radiation belts. And I think that's the end of what I wanted to say. So if you have questions, I'll be happy to take them.
Thank you so much. Thank you, Dr. Holzworth. That was a really fascinating presentation. We are ready to start the question answer session. And as a quick note, the reminder of how to do this is that if you're joining by Zoom, please continue to ask questions in the chat, as many people have already done. If you're joining by phone, you will need to raise your hand by pressing *9 to unmute yourself. And then when you're finished, press *6 to remute yourself. If we run long here, Dr. Holzworth has offered to continue to be available for several minutes after the top of the hour to continue discussion as needed. We do have some good questions. Dr. Vanarugud Nagaraju, I hope I'm pronouncing that right, has shared several bits of information of papers from India. He's at the Satyabama Institute of Science and Technology in Chennai, India. And if you all take a look at the papers that he's referring to, one is called Detecting Lightning and Thunderstorm over Global or Regional Scale Using Remote Sensing Observations and Quantifying Their Variability in Changing Climate. And then also Detecting Convective Clouds over Tropics Using Multispectral Satellite Observations and Quantifying Their Variability. So really appreciate that networking effort and information. And I hope that I hope that Nagaraju can share links to those in the link in the chat as well. Suleiman Ali writes and says, hello, I have a question. Are there any other regions that also show similar findings in the Arctic where lightning increasing due to global temperature mean, such for example, in the tropics regions or other regions?
Oh, that's a good question. As I mentioned, the Woolen network has been increasing its detection efficiency and still continues to do that a little bit. So the answer for global is we don't have the resolution yet, or at least we haven't processed our data in a way to be able to suss out the resolution to suggest that there is a significant increase in global lightning. Some people suggest that that's the case, but I think the data are still questionable because of the problem with the variability. There's a lot of variability, and so it's hard to say whether the globe has increased or not. But as I showed in one of these figures, the total number of strokes that we see in the Arctic hasn't changed very much. Actually, this is the total global Woolen strokes for the whole globe for June, July, and August over this 10-year period. And so this is part of the answer to your question. The total global lightning hasn't varied very much. Okay, maybe 10%, I don't know. But certainly any variation that is global that shows a trend would be buried in the data that we have looked at so far. However, I can add that we did look carefully at the, in this paper I discussed just north of 65 degrees north, but we also looked at bands from 45 to 55, 55 to 65, and then above 65. And the same exact variability that we see in the north of 65 is also seen in those bands. That is to say that in each of those bands, from 45 degrees to 55 and 55 to 65 and 65 to 75, increases and decreases just like more or less in the same pattern. You can see that if you look at the paper that I mentioned, the GRL paper that we wrote on this topic a couple of years ago. There's a supplementary. There's some supplementary information, and it shows those those plots for the latitude bands, and they are also increasing. The only thing is we just don't have the resolution, or the variation isn't that much, and so forth down below 45 degrees. Most lightning on the Earth, vast majority of lightning on Earth occurs between plus or minus 45 degrees. And so a reduced and reducing amount occurs north of 45 degrees. And once you go south of 45 south, there's almost no lightning after you get to minus 55. And over the Antarctic, you certainly don't have enough to do statistical studies of how lightning in the southern oceans and over Antarctica may or may not have been varying, because there's just not very much lightning down there. So you don't have the kind of data set that we have for the Arctic to study the statistical variation in overall. Does that answer your question?
I believe that did answer that question pretty well.
Okay.
And if they will continue to use the chat for following up. Janet Warburton asks, have you seen lightning during winter months in the Arctic? She has heard of snow, thunder, and heard it once in Anchorage, Alaska last winter, and just wondered how frequent is it now in the winter months?
That's a good research study. We focused on the summers when there's enough data to do statistical studies, and it's highly likely that we will see that we do see some occasional strokes in the high latitudes from convective activity that occurred even in winter. Although I might say that the when it's snowing and you get, thunder snow or something like that, those are probably occurring from lightning discharges that are from relatively low altitude to ground or in cloud, and they're going to be less easily visible, I would guess, than the typical lightning strokes that we see from regular convective clouds. So I don't know the answer to your question, and it sounds like a nice topic to dig into, but I doubt if we have statistics to be able to say anything statistical about it other than just, oh yeah, we have an event here and an event there.
Thank you. The next set of questions is from Amber Soya, and she asked at about 9:20, what is up with Greenland, the lack of lightning, and what are the reasons northern Eurasia would have so much more lightning? Is this related to the largest increase in temperature changes that are in northern Eurasia? Thinking of Greenland and the Arctic, parentheses, water/ice, as opposed to continental northern Eurasia, is this part of your explanation? What is that mechanism? Thanks for the thoughts. And then she writes later, thanks, this is making sense. Differences between cold and warm is the power force that is driving the convection and lightning. So you might want to follow up on that. Thank you.
Yeah, no, that's absolutely right. Over Greenland, you have this vast expanse of ice that is not going to be allowing you to have differential heating. It's all the same temperature, or at least it's all cold and the not very much not very strong pressure power to drive convective activity. And so over Greenland, you just don't have a lot of convection that would cause you deep convection that would cause thunderstorms and lightning. In order to get lightning, generally speaking, you need to have ice interactions in the cloud. So the typical lightning at middle and low latitudes is caused by charge separation that typically occurs between about -10 degrees altitude and -20 degrees altitude in the cloud. And that's a region where you have multiple kinds of ice. You have ice that's frozen by vapor deposition, like snowflakes. You have ice that's frozen by riming. So you have rimed ice, and you have some super cool water. So you have liquid water and you have two kinds of ice. And that's the region which is the strongest charge separation region. And so if that region sort of disappears, or the temperatures already start at -20 at the ground and get colder as you go up, you just don't have the regions where you have the kinds of ice and water development that allows for effective charge separation. And then also you have sort of a uniform temperature, relatively speaking, over the region that doesn't allow for the small scale. Thunderstorms are typically, let's say, 5 or 10 kilometers across, a typical cell of a thunderstorm. And so you need to have differential heating that's on that same scale. So you need a region that's colder and next to a region that's warmer, and then the warm air will be rising and causing a convective activity, a convection, which then gets amplified by the cloud dynamics, and it can develop into a thunderstorm. You just don't have that over those icy regions. So that deduction of yours is correct.
That's a great explanation. Thank you. Suleiman Ali asks, does South poll also show increase in lightning strike, which I think you've covered. And do you consider other data sources such as Earth Network or GLD 360 lightning data?
The answer is, as I mentioned, as you noted, we just don't have very much data there. We have not measured very many strokes in Antarctica. And those for two reasons. The main reason, I believe, is the same one's why there's not a lot of lightning in over Greenland, and that is the southern continents are covered by ice almost completely, and so it inhibits convection. The other problem with ice over the Antarctic is that radio waves in the VLF don't propagate as well over ice as they do over water. So you'd only be able to see the really strong strokes, although there's always a lot of strong strokes in a given convective cell. So we would have expected to see more lightning. However, the propagation effect may have caused some decrease in our ability to actually detect lightning if it were over the southern, occurring over Antarctica in any real way. Although, as I said, we have 5 stations down there along the coast, and that's going to help us locate lightning, especially if it's inland, measured by hundreds of kilometers as opposed to thousands of kilometers. We should easily be able to see that, and we don't. So we just don't see a lot of lightning down there in Antarctica. What was the other part of your question?
Do you consider using other data such as
other data?
or
Yes.
GLD 360?
So you should know that all the Woolen data are delivered in real time to our partner, Earth Networks, and becomes part of ENGLN, Earth Networks Global Lightning Network. So ENGLN has Woolen data in it, as well as ENTLN, the Earth Networks network data. And so that's all combined into the Earth Networks ENGLN data set. So yes, we certainly constantly compare and look at the Earth Networks data. And I don't want to, I have not done comparisons. Other people have done comparisons with the GLD 360. The Woollen data set is produced and managed by universities, and anyone can buy it at a nominal price. You get a whole year of Woollen data for just $500-600, and that's not the case for the data from other networks. And so we have not done the kind of global comparison that you might want to do, and so the answer is there's likely to be some differences, but there's been a few regions where we have jointly combined with GLD and written some papers studying particular regions, like some of the events associated with volcanoes and things like that. And Woollen sees more or less strokes in a given location than GLD 360. So I don't know globally the differences that you can. I will say that Woollen provides in real time for everybody our relative detection efficiency. Anybody can look it up. It's on the web. The relative detection efficiency is available to everyone in a 1 degree grid for the whole globe every hour. And so you can see what the network's doing and how the relative detection efficiency is varying over our network. And so I don't think we have that kind of high resolution information from anybody else.
Thank you. And I think you just covered the follow-up questions from Anomaly, which was the accuracy of lightning strikes locations from Woolen system. Another question that came in from Randy Jant is related to the first part of the last question, I think. Is the water conductivity the reason for loss of sensitivity in interior continental Alaska, where Woolen apparently detects only a portion of strikes recorded by agency lightning detection instrument arrays? Can I reread that?
No, I think the answer is no.
Okay.
And so certainly propagation across the continent is there's a higher attenuation coefficient than over the oceans. That's true. But we have stations in Alaska. We have Anchorage, and we've had stations on and off down in the Aleutians, and right now that's not working so well. We have one in Fairbanks. So I think that the answer is that there's, just like the rest of the lightning in this study, once you get north of, sort of the middle of Alaska, there's just less and less lightning up there, more and more ice, more and more frozen tundra that lasts year round, and so forth, as you go further north in Alaska. And so you allege that there's a difference, and the only difference I've seen with the network that's run by the BLM, I think, or somebody like that in Alaska, is that the spatial resolution of that network was really bad a couple of years ago. I don't know what it is now by comparison. So I don't actually know the answer to your question for current lightning in Alaska. It'd be an interesting study, but I don't think it's related to loss of significantly related to loss of signal by propagation attenuation over the continent. I think that's possible, but the continent, the region of Alaska is not large enough to totally eliminate the signal. Even in at the South Pole, it's not. Antarctica is not large enough to completely eliminate the signal. I have a nice data set from a balloon flight, which we flew right over the South Pole, and we measured VLF signal all the way across there, and we can see it attenuate as we propagate into the interior of Antarctica, but it doesn't go away. Anyway.
Thank you. There are no specific questions remaining. I want to refer everybody to the sharing of citations that has happened in the chat, which has been wonderful to see people sharing information like that. And Van Ganaru Nagaraju shared his email contact, or the email contact, which is nagav, NAGAV 12345 @gmail.com. For those of you who are leaving now, we'll do a quick close. We want to thank, of course, Dr. Holzworth and all of you for a great presentation, and everyone that's joined and been so active in communication. Today's webinar will be archived and available on our seminar series page, which is www.arcus.org/research-seminar-series-archive. And an email containing these links will be sent once the video recording has been posted online. You can always visit the Arcus homepage for more information about Arcus, our programs, and upcoming Arctic-related events. We continually work to improve our seminar series and look for suggestions for future seminar topics and speakers. Please do take a minute or two to complete our short survey. A link to that is available now in the chat window. The link is a SurveyMonkey, so www.surveymonkey.com/r/7SC. And I'm not going to share that. I'm not going to try and read that off. But anyway, you'll receive a link once the seminar has been posted to our webpage. We do invite you to join an upcoming webinar on Thursday, the 14th of April at 9 a.m. Alaska Daylight Time. Denver Holt from the Owl Research Institute will present a webinar entitled 30 Years of Snowy Owl and Lemming Research at Uktiavik, Alaska. Research for that seminar will be available soon. I do not see any further questions, but for those of you who are staying online, you could ask a few. I see that many folks are saying thank you very much and enjoying the conversation and the presentation quite a bit. I believe that unless there are are there any final questions for the presenter, for Dr. Holzworth today? We've got a lot of thank yous. And again, people have shared great information with paper titles and links and emails in the chat, and we hope to be able to share all that. Dr. Holzworth, thank you very much. Is there anything else you'd like to add here at the very end?
No, it's been nice to be able to sit in my desk at home and give a seminar that is seen by several people, actually around the country, maybe around the world.
Around the world, I believe. I think we've had folks from around the world. Yep.
Yeah. So that's very nice, and I'm glad to. And also, one of my slides, I gave my email address. Please don't hesitate to email me if you have questions. I'm happy to talk to you on email.
Well, thank you very much. Then I believe that this will conclude today's webinar. We really appreciate the participation. Again, the great presentation by Dr. Holzworth. And we wish everyone a great day and have a good weekend as well as we start daylight savings time this weekend. Thank you.
Thank you.
Bye-bye.